Hello, 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 everybody at home. Let me go turn on the light. Let me go turn on the light. Guys, spring came. Weather is amazing. Yesterday it was raining all day, but today now it's getting sunny. It's not sunny. We have some clouds in the sky, but I was outside and it felt amazing. Don't miss it. Don't miss it. I went to the public garden. Like squirrels come to you and they just climb you. I didn't have anything to give them, but it was so cool. Like at one time there was one on my hand, one in my jacket's hat. I was scared. Like if I moved, they bite me, but they left me alone. Now let's get back to business. La 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 la. Because you may say, why should we get back to business? We wanna code. Yeah, okay. Last time we talked about it. Seems the revenue part is not fully updated. Therefore, we have to, like, even the proposition is not true. So we need to be more cautious. We need to be more cautious about how we are going to implement the code. I'm launching my Anaconda. And then I also want to launch Overleaf to see the proof. Even the proof is not completely complete. Oh, I don't have internet, that's why. Not internet case. MIT secure it. Pure. Okay, Jupyter Notebook, as we all know, RStudio, Spider, none of them. No. We are Python developers. Know who you are in life. We are Python developers / mental masturbators / armchair theorists / I don't know, the rest doesn't matter. When I'm doing my coding, I don't give a fuck about the rest of the world. Nothing can stop me from writing my function. My dataset is everything to me. When I code like I am walking in my dataset. Every cell, every column, every row, I'm looking at them and they are looking at me back. That is the level of connection. Every digit matters. Research, Gaussian. Okay. Revenue maximization. As I see in Corollary 3.14 in the highest expected payment. Since mu AI is pinned down by the obedience constraint, this objective function is concave in decision variables, the covariance coefficient, over the set of incentive compatible mechanisms for which we also have Thus, it follows from lemma d6 that we can restrict ourselves. This is the problem we are dealing with, guys. We have to go over the proof in a way. I know we already have the proof, but we want to get our hand familiar with the proof, because the proof is not, I haven't done the proof, this proof, so why did I do that? Oh, okay, Thibaut is here too. Let's see what we can do. This is what I want to do. I want to maximize sigma area squared. Make sure that maybe I need to share it with you, huh? This is my code. To be honest, okay, Thibaut's code, I can see that it is more advanced. Also, he's following some guidelines to make your code readable. I don't know if it's necessary. I like to do my code dirty. I just care about my curves. Maybe I start the code again from the beginning for myself, the same way I did for my benchmark. And it probably won't take as much time. Sigma AI squared, guys, let's focus. Oh, I need this. I want to share it with you guys. Why don't you Control Shift 2? I want you to be with me. Make myself smaller. Look at my dedication. Wow, airplane flies so straight. Not dedication. What is it? Alright. So you see that? Okay. Actually, I shared in a bad moment. Fuck you guys for a second. I have to look at the. Okay. So max sigma AI squared minus T sigma AI theta I minus T. This mu AI squared, mu AI is pinned, guys, by mu theta I and mu omega. So don't look at it as a variable. It's already pulled down. It's already taken. Sigma I theta I. Sigma I theta I we can change. We can see subject to what are the constraints. Even sigma I squared is pinned down, kind of sense, by obedience. So 1 over, once we get into the proof, you can see the details better. Sigma theta I squared. Sigma AI theta I minus sigma AI theta j. Sigma I minus theta I minus sigma AI theta j squared. Just that. What? This is not true. Is the first the PSD we had? I guess it is. I thought we had, yeah. Sigma A squared minus sigma AIJ came to me very weird. As sigma theta I squared. Let's write this motherfucker down. Sigma AI theta I plus n minus 1 sigma AI theta j squared plus n over sigma omega. Omega is w sigma p sigma AI omega squared. What's that? Or equal sigma AI squared plus n minus 1 sigma aj minus 1 sigma ai aj. Now I want to make it look better, so I make it smaller. First constraint, second one, what is the third one? Sigma area squared equals n minus 1 r sigma area j. Oh, guys, I need to do a back day now. I can feel it. Yeah, sigma area omega. Always put your back day right after your chest day. Best combo. Well, the best combo if you don't have any chest day, to be honest. I think it is a sign of getting mature in life. It is a sign of getting mature in life. Once you have more respect for your back day, for your leg day, than your chest day. Shoulders still matters big time. Big time. And then sigma a. Plus 2 sigmas. What is the, how do they say it? Getting matureness? We are just going in this one to check matureness. All right. Maturity. Yeah, that was not so difficult to guess. Maturity. All right. Do back day. It shows your maturity has been arrived. And minus 1 r sigma a theta I. Also leg days, guys. Your hips, glutes. If you like hip thrust more than squat, it shows you're getting to your maturity phase. Okay. It shows you got so many injuries. Sigma theta I squared and minus 1 r theta j. So these are the constraints for them. Let's go to the proof. And we know f is 1 over n minus 1. And, oh, okay. I minus, okay, I agree. We have, I like the objective here, max. Once we substitute sigma ai squared by the term we have, so n minus 1 r sigma ai aj plus s sigma ai omega, the t and t goes, minus t mu ai squared sigma theta I squared over sigma AI theta I. And then what are the constraints? Now we want to remove probably sigma AI theta j and sigma AI squared. All right. So this part, what is it doing? Let me open a yeah, let's also check the computations. It's very nice to do that. Yeah, you can join me here. So I want to make it bigger here. Okay, add a page here. So this term on the constant. Okay, fuck that. 1 over sigma theta I squared sigma AI theta I minus sigma AI theta j. It comes from this one. So what should I say? Sigma AI theta j is 1 over n minus 1 r sigma AI theta I minus t sigma theta I squared. That's it. Squared less than or equal n minus 1 r minus 1 sigma AI aj, right? Plus s sigma AI omega plus t sigma AI theta I. Does it look anything like the one we have? Can be. Yeah, let's play with it a bit. So what can I write here, right? So we have 1 over sigma theta I squared. That's good. Sigma theta I squared. What I want to have is sigma, okay. 1 over n minus 1 is, and let's also times it by r squared. Multiply it by r squared. Yeah, like pull the r squared out of it. So if I want to say that, what happens? 1 over r squared sigma theta I squared. So we have r squared for this one, and this has fr. So we have r squared minus fr sigma AI theta I. Oh, it has one r inside it. Okay. So it will be r minus f. Plus t ft sigma theta I squared less than or equal. How do you want to write the other side? S sigma I omega T sigma I theta I minus how does it minus n okay n minus 1. I don't get this part. Is it the same term? N minus 1 r minus 1, is it equal to minus n minus 1? Oh, because we have an n minus 1. Okay, f minus 1. It's not nice to have both f and n minus 1, but doesn't matter. Yeah. Alright, dogs, we just need to check this term. This equality here. This one. So this equals n minus 1 r minus 1. Yeah, they're the same. Okay, so the first inequalities are right. So the lesson I learned from this time getting injured and going to therapy is that you want to keep your core engaged, like all of the time. All the time you want to keep your core engaged. You're sitting down, you're standing up, don't use your back, use your core. Like your core should be connecting your upper body and lower body. Plus is sigma AI omega minus mu AI squared T sigma theta I squared over sigma AI theta I, right, subject to 1 over r squared What about the second constraint? Does it make sense? No, I want my charger. Fuck. My iPhone, my tablet is going out of charge. Alright, no problemo. No problemo. Second one says let's copy all of these. Here. So that's can easily use it. Sigma theta I squared. Sigma AI theta I remains. Sigma AI theta J, we want to change it. N minus 1 times that will be 1 over R. Sigma AI theta I minus T sigma theta I squared plus we want to keep sigma AI omega. It will remain one of our optimization variables. Sigma AI squared, we don't like it, N minus 1 R sigma AI AJ plus S sigma AI omega plus T sigma AI theta I, and plus N minus 1 sigma AI AJ. Now let's look at what we have here. Okay, we have again R 1 over R sigma squared sigma back straight sigma theta I squared R plus 1, right? Yep. R plus 1 sigma AI theta I minus T sigma theta I squared. Sigma theta I squared sounds good, squared plus N over sigma omega squared sigma AI omega squared less than N minus 1 plus R sigma AI AJ plus S sigma AI omega plus T sigma AI theta I. Right? Is that right? R squared sigma theta I squared 1 plus R sigma AI theta I minus T sigma theta I squared N over sigma omega squared sigma AI omega squared N minus 1 plus R sigma AI J T sigma AI theta I sigma AI. Alright, we are all good. Squared sigma theta I squared make me a bit bigger. R squared sigma theta I squared 1 plus R sigma AI theta I minus T sigma theta I squared plus N over sigma omega squared sigma AI omega squared less than equal S sigma AI omega, this term, two term repeat, T sigma AI theta I, right, plus N minus 1 plus R. So you can see we have F minus R in the parentheses and 1 plus R, which gives us the interval for the values of R that the optimization problem do not blow out. Sigma AIJ. All good. And what else? What else do we want to know about this? Then we introduce the Lagrangians, for sure. First inequality matches, and we also, for now, forget about the one that comes from IR, lambda mu chance. So where is the first one? I think first one comes from taking derivative with respect to sigma aij. So if I wanna do sigma aij, I will have n minus 1 r plus lambda minus n minus 1 f minus r and plus mu n minus 1. Oh, we're using a new, right? N minus 1 plus r equals 0. If we get rid of the n minus 1, can I show you here? No, but I want this one big. Now I can show you this, right? Sounds good. That's nice. Okay. So we have this r plus lambda. Okay, he has minus sign. R plus f minus r lambda plus minus 1 plus r nu. Sounds good. Checked. What is the other one? Second one is respect to probably sigma ai omega. So we have s. From the first one we have lambda s. From this last one we have mu s minus mu 2n over sigma omega squared sigma ai omega equals 0. So what it will be, minus s minus lambda s plus nu 2n over sigma omega squared sigma minus s. Sounds right. Checked. And for the last one, we have sigma ai theta I. Or x minus mu ai squared t sigma theta I squared to be plus 1 over sigma ai theta I squared plus t lambda minus lambda over r squared sigma theta I squared 2 f minus r sigma ai theta I minus ft sigma theta I squared. right? Plus t times mu, let's use nu, t times nu, and minus nu over r squared sigma theta I squared 2 1 plus r sigma ai theta I minus t sigma theta I squared. That's it. So what do we have here is, okay, the whole thing equals 0. Now he's saying mu ai t sigma and over sigma squared t. So we are keeping these ones on one side. Which one is the other? Okay, these are on that, and then move the other two to the other side, which will lead in 2 lambda over f minus r squared sigma theta I squared f minus r sigma ai theta I minus ft sigma theta I squared plus 2 nu over 1 plus r squared sigma theta I squared 1 plus r sigma ai theta I minus t sigma theta I. Sounds good, right? So our Lagrangians are okay from the first. Oh my god, my leg. I should not look at my phone. I just want to know what time it is. Okay, 4:36. Let's go. Let's continue. These are all correct. Now I want to know the nu and sigma a omega. They are correct. I don't want to check them again. Is negative. Oh, this is just for R negative. Denominators in the problem. Well, we still can't think the problem is being solved for R negative and positive. When if R is positive, the problem is that maybe nu is not. Now nu is. Do we have lambda? We don't have lambda. Denominator positive. Let's assume lambda is non-negative. So everything well defined. Nu is positive, meaning the second anti-correlative PST is binding. So the second inequality will be equality. This one, which gives us sigma AIAJ based on sigma AI theta I and sigma AI omega. Substituting the expression for nu in the last equation, we obtain this. Okay, the last equation, where is it coming from? Sigma AI theta I. So we have these three from the stability. From this one, we can also compute sigma AI AJ based on sigma AI theta I and sigma AI omega. Now we have nu. Do we have lambda? Okay. Sigma AI omega is also computed based on sigma AI AJ. We can have it based on, okay, what are the things? Nu just came from the stability. Based on lambda as a function of lambda. Sigma AI omega, the same thing, function of lambda. They are from the first two stability constraint. We will keep the third one stability, okay. Now nu, it's not nu, it's lambda. Nu being greater than 0 gives us KKT, and anti-correlative is binding. Therefore, we have sigma AI AJ, by instance sigma AI omega, and sigma AI theta I. This one is already computed here. So the only things that are left are 1 sigma AI theta I, 2 lambda, 3 third in stability, which is this big equality, right? We have this big one here, and okay, we have everything else, like in this inequality, based on lambda. Sigma I theta I want to keep it. Sigma theta I, nope. R nu, I will change it based on lambda. Sigma I theta I will keep it. Nu, I change it. Mu AI, it's a constant based on t mu theta I. We have it. So we will have, once we write all of them, have a big equation. It's a very big equation. It's like this big. That left is like 4 sigma AI theta I, connect sigma AI theta I and lambda together. But still we are missing something. Right? Even if I have sigma AI theta I as a function of lambda, what is our lambda? We want to have the optimal solution, right? What is the lambda? That's what we are going to continue. Note that because R is negative, sigma AI omega is already a function of lambda, by the way. Note that because R is negative, the denominator in the previous expression do not vanish for the. So he substitutes everything. This is the big equation we were talking about. Everything is sigma I theta I or lambda. The rest are parameters, external parameters. Mu AI is also pinned down. Words, now we are changing sigma I theta I to sigma I theta I over T sigma theta I squared, because it is a variable that shows up everywhere and kind of scales the element of sigma I theta I. So it's x. Now we have a linear term, right, on the left hand side. F lambda of x minus g lambda equals 1 over x squared, c over x squared. Great. In other words, this is, but what is our f lambda? F lambda is 2 over r squared, lambda nf f minus r, 1 plus r. G lambda is 2 over r squared, lambda nf f minus r plus, minus g lambda. So lambda nf minus r, 1 over r. What is our c is mu I squared over t squared sigma theta I squared. It is easy to verify the assumption of lemma 5, 6 are verified, and equation for this does have a unique solution x lambda in the interval. So this is a degree 3 equation for x it has a unique, degree 3 can have 3 solutions, right? But either the 2 others are negative or they are imaginary, and therefore x lambda, we have a unique, real, non-negative solution. Notice we want our x lambda, by the way. That is something we said, let's relax for now. X lambda should be greater than 1. That comes from IR. We will check it later though. Furthermore, once we increase lambda, x lambda decreases and goes to g lambda over f lambda. What happened here? X lambda it means that kind of this will be 0, right? But it means in a sense that x lambda should go to infinity, doesn't it? I don't like this one. Where is this coming from? Over f lambda. If it is going to this, which is g lambda over 1 plus r squared over 2 1 plus r f minus r, if it is going to this number, okay. Why do I expect that? I expect that because you expect the solution to a degree 3 equation is a continuous function. Yes. Solutions of a degree 3 equation should be continuous function of the coefficients of the degree 3. So it should be continuous function of f lambda, g lambda, c, x lambda, right? And on the other hand, f and g are continuous function, c is continuous function of lambda. I don't agree with this term here, to be honest. Let's go over lemma. It doesn't. I think if this limit is this, and I call it L, then L is the solution to actually x minus, anyway, f infinity L minus g infinity should be c over L squared. But here they are saying fl minus g0. What? Unless f and g are kind of going to infinity with lambda. Is it the case? So when f, yeah, it is, okay. All right, now it makes sense. When lambda goes to infinity and r is negative, guys. Yes, that's true. F goes to infinity. When g goes to lambda goes to infinity, g goes to infinity. So it can be still true. I cannot do the I cannot multiply the equality by f because both of these two guys are going to infinity. This one as well. So it's possible. Beautiful, beautiful. Okay, let's check lemma 5.6, but let's see if we got any emails. We didn't. Maybe. They're good. Lemma 5.6. Okay. Okay, consider the following parameterized equation in the unknown variable x. B lambda x minus c lambda y over x squared. Assume a greater than 0. What is our a here? Our a is c, which is mu ai squared over t squared sigma theta I squared, positive. And b is positive and increasing for some interval. B, are you positive? Yeah, when lambda gets big enough, it is positive and it is increasing. Agreed. For each lambda in R, define C lambda x tilde for C lambda over B lambda and assume x tilde is decreasing over. Is it? We have to check this one. It's not obvious. So, is it decreasing? Let's check it. G is G lambda where F lambda equals 2 over R squared lambda in F minus R plus lambda in F minus R 1 plus R over what? 2 over R squared lambda in F minus R times 1 plus R. That's it. So, is it decreasing in lambda? So we have lambda in F. We have lambda in F. We have 6% charge. We have lambda in F. 2F minus R. What is the name? 2F minus R over R squared plus 1 over 1 plus R minus 2 over R minus plus R. Agreed? I say that's it. Alright, over lambda in F. Okay, we have 2 over R squared, that doesn't matter. Something like that. F minus R. Fuck, the same thing. So if you have AX, x plus b over 6 plus d. The derivative will be minus so the derivative sign is all about AD minus BC. What is the AD minus BC here? A 2F minus R. Oh. Copy. AD. What is D? It is D. Minus B. What is B? These are the moments that actually I think like you want to do these computations. I think it is the best moment. Do it with somebody else, like with your colleague, because they see that you're working. And these are the parts of the work that takes time but brings not a lot of results. So you want to be seen that you are doing something, but yeah, it takes time, and it doesn't require you to think. Once you're thinking, you want to maybe just walk, you want to sing some music, you want to be loud. But once you're doing this stuff that takes no brain cells, it's better to do it next to somebody else. All right, is it positive or negative? So it will be negative sign and negative sign. And seems it is very negative actually, right? You don't need to compute it. The whole term here is positive. Yeah, R is negative. The whole term positive. This term here is negative though. So the whole term is positive. This term's negative. This term is negative. So if we have I cannot say now, because we have a positive, negative. We cannot say what the fuck it is. Where is this negative sign coming from? Yeah, I don't want this. Oh, actually, I did it wrong. Okay. Minus this, and that is just F minus R. Maybe now we can say what's up. So this we don't know if okay, this is negative. This is negative, right? This is positive. This shit is positive. This is positive, so the whole thing is positive. This will be positive, right? So it is positive minus positive. Again, we don't know what's up. So I should compute and see what's up. So we will have f minus r factored out minus 2r 1 plus r over f minus r minus 2r 1 plus r squared. All right. Plus 2 over r plus r over 1 plus r minus r. That's it. So we have f minus r minus 2 1 plus r over r plus 2 over r plus r over 1 plus r minus r. Then I can say 2 over r and 2 over r will go. So we will have r over f minus r minus 2 plus r over 1 plus r minus r. So this is definitely negative now. Oh fuck, no, we still don't know. Because r is negative. This is negative. Should see what it is. Minus 2 minus r. How do we know if it is negative or positive? Okay, if this ratio is decreasing, right? C lambda over B lambda is decreasing over I. So it should be negative. It should be negative. Right? Is this negative though? Is it true? How do we know that? When r goes to 0, yeah, it is negative. Well, when r goes to 0 or r goes to minus 1, they are true. Fuck it, we should do that. Minus 2f plus 2r plus f minus r times r plus r. Is it true? Yes, this is true. right? This is negative, this is negative, this is negative. Yep. Okay. Decreasing. All right, we're good. Okay. Should I look at my phone? Just a glance. What? So it is decreasing. Then for lambda, like big enough, has a unique solution in the interval. Oh, x in the interval. Alright. So once lambda is big enough, we have a unique solution. For each lambda in I, x lambda, which is the real solution, will be bigger than the c lambda over b lambda. So here also we know that here when we say, I don't know why we say when x lambda goes to infinity, it equals to g lambda over f lambda. We know that x lambda is always greater than g lambda over f lambda. But what is the other inequality that says x lambda is kind of sandwiched? Well, we can say, okay, one thing we can say is, right, it should not be that difficult. You know, x minus g over f equals c over x squared f, right? So x equals g over f plus c over x squared f, which is greater than, once lambda goes to infinity, f and g go to plus infinity, by the way. Keep in mind, it's greater than g over f, right? No, I want to say this term goes to 0, which is obvious. Actually, this is true. X lambda, take lambda to infinity, this term goes to x infinity, this term goes to the x, this term goes to 0. What's wrong about this? That's right. X is bounded, f goes to infinity. This is right. Oh, x is not bounded. Okay, I don't know. Something like that. X is decreasing over I. X is decreasing over I. Interesting. X tilde is also decreasing. Look, x tilde, this is decreasing. X is decreasing. B lim sup of is infinity. Then it will be greater than 1 all the time, which is great, which says our IR that we said let's forget about it for a while will be satisfied. And lim sup of x lambda. What is x lambda? G over f. G over f, once lambda goes to infinity, goes to that was a big lemma. Interesting. G over F goes to lambda goes to NF over 1 plus R plus 2 NF F minus R 2NF NF minus R over R squared over R squared, the whole thing over F, which goes 2NF F minus R over R squared. So we can remove the NF. No bueno. Oh, all bueno. Will be 1 plus R squared 2F minus R 1 plus R, which is the term we have here, right? 1 plus R squared 2F minus R. Alright, everything sounds good. Very interesting. We may go read the proof of the lemma later. So x lambda goes to this. Let's take a sip. So let's go over why did we do all of this stuff, right? We had a degree 3 equation, or C over X. We did the Lagrangian, right? We did the Lagrangian. We computed everything based on lambda. The only thing that was left to be computed was sigma ai theta I, or x equivalently. To compute them, we have this degree 3 equation, and for that we have this lemma that is telling us x, or sigma ai theta I, has a unique solution in the positive interval, and we also know the limit of it when once lambda goes to infinity. So for now we know that it has just a unique positive solution. That's what we all care about. But lemma gave us something more. The x is greater than 1, which is amazing, meaning that our IR is already satisfied. The solution to this equation. So we can also all of this says that we can also compute sigma ai theta I based on lambda. So everything we can compute it based on lambda. But what is lambda itself? It is still remains. What is lambda itself? So sigma ai theta I, you have sigma ai theta I based on lambda. Good. From the equation f x minus g equals c over x squared. It gives us this. But what is lambda itself? Where should we find lambda? We had KKT, we used, is lambda positive, by the way? Well, lambda is non-negative, but if it is 0, if it is positive, it means that the first inequality is also binding. which means the solution will be deterministic. I don't know if the solution is deterministic or not yet, because remember, the proposition is not correct anymore. It needs to be updated. How can I find lambda? I have everything based on lambda. First stability gave us nu based on lambda. Second one, we used obedience so far. So forget about obedience. Obedience gives us nothing. First and second PSD. We used 3 stability Lagrange multipliers. Sigma Aij comes from the KKT. So we have another KKT too. Either lambda is 0, lambda 0 meaning it is the situation we can add some noise, and the first one is not binding. Lambda being positive, but what is the lambda? Where is the equation that gives us lambda? I want that. KKT so far, nu was positive. Okay, KKT didn't give us the big equation. Big equation came from this third stability one. We computed sigma A omega, sigma A omega and sigma A theta I. What is left to compute lambda? I'm kind of lost. I forgot. Let's go back before going forward. We have this equation. Look, now everything is based on lambda. So this one gives us nothing new. This one gives us nothing new, right? This one we just solved it based on lambda. Where is the other one that gives us something? So either lambda is 0. By the way, okay, we know this one. Lambda times the first inequality should be 0. Okay, we know this one. All right. KKT 1, right? Lambda, the inequality should be okay. RHS minus LHS should be 0. Either lambda is 0, we have first inequality strict, slack, right? Which what it means. What does it mean once it is slack? Okay, once it is a slack, it means max objective is function of sigma I theta I subject to another function of sigma I theta I less than something constant, and then you can do it, right? Lambda is 0, by the way, so it sells a lot, like we have a lot of parameters solved. Or lambda is greater than 0, then the first one is binding, and we have another equation from which we have a function sigma A, we have a sigma A theta I of h of sigma A to 0, and from that we can compute sigma A theta I of lambda. Probably then we can't compute lambda. Well, that's what I wrote. I think you cannot see this because I am at the corner. Now you can see it. Right? Sounds good. Either lambda 0, do whatever you want. It will be simplified, right? We have this nu simplified minus r over 1 plus r, everything can be simpler, right? What happens if lambda is 0 here? 2 over r, these terms, a lot of this, then you can compute sigma A theta I easily based on lambda, and then, not even based on lambda, sorry. When lambda is 0, what happens in this inequality? If lambda is 0, what happens? Lambda 0 gives us 2 over r squared x minus r 1 plus r. We have like an extra inequality then. Plus 2 over r equals mu ai squared t squared sigma ai theta I squared 1 over x squared, right? What is the solution to this? This is also similar. Again, what is it? Oh yeah, it is. So again, we can use the lemma, and well, lambda is 0. Lambda is 0. It has a unique solution, we know that, right? So for lambda even 0, we have a unique solution. Why am I talking about lambda being 0? Oh, we want to see if once lambda is very small, are we inside, is the inequality binding or not? Doesn't need to bind, right? If lambda is positive, it is binding and everything. So it's just a 1 point. I don't care about it, to be honest. Okay, good. Let's continue. Let's continue. It's so windy. Since 1 plus r was negative, okay, this is generally true. By assumption, we get that this be positive, second inequality is binding. 3 point, this implies that action anti-correlated maximally. What form of proposition? The form of the proposition is not right, by the way. What are you talking about? Oh, okay, this term here, anti-correlated. So that is alright. Then everything will be a function of delta. Okay, there was one point that Thibaut told me after that the proof is not complete. What is that point? Guys, if you don't like a bar, don't go there. Or don't go there often. Okay, fuck, every time you look at your phone, you should be ready, guys. Don't forget that shit. Every time you pick up your phone, be ready. You are going to find something there. You want to find something. But there are thousand other things that distract you. You should kind of go after what you want, your eyes closed. If you open your eye, you are probably at the wrong space. Okay, now I want Thibaut. Maybe the only thing that does not distract you is your email. Inside email, nothing big happens. For convenience at the end of the proof. Where is the for convenience? Somewhere we should furthermore. Okay. Oh, okay, this part. It's barely charging my phone. Guys, let me pause it for a second. Yeah, I will pause it from here. What is happening? Back. Okay, let's go finish the proof. Where were we? Okay, G lambda over F lambda, since this, by assumption we get that this, and the second inequality constraint is binding by completeness. This implies action correlates in other words, most of the time lambda is positive. Or I don't know. Point is inside the ellipse. What ellipse? I will show you what ellipse. Where is it? This is for 11. This is the ellipse. No. Yeah, let's remove sigma ij, then call it ellipse. What ellipse? Okay, let's call this motherfucker ellipse. Yeah, this is an ellipse. This is an ellipse. This one is an ellipse. Sigma I theta I and sigma AI omega based on sigma AI theta I. Is it an ellipse based on sigma AI? How is it an ellipse? It has no square term based on sigma AI omega. It doesn't have any term based on sigma AI omega squared, unless what was sigma AJ we had before? So we compute sigma AJ based on the second one, and once we put back it here, we have an ellipse. That's the case. Otherwise, it looks more like a parabola. What is the ellipse? I don't know. Structure. Ending by completion is Magnus. In our structural result, let's go over the structural result. This is the part we added newly. This is it. So P is on the curve based on the equation we have for lambda. What is it? P changes by lambda. What is this? This comes from the obedience. No, obedience applied to PSD. PSD applied by obedience. I don't know which one is which. Okay, I wasn't here for something else. I was here for structural results. If you could read it for us, brother.
We explore in this section the consequences of our characterization of obedience, section 3.2, for optimization problems and present general results on the structure of maximizers of an arbitrary concave objective in the class of obedient mechanisms. Problem setup. We denote by O the set of all pairs, mu, k, in which mu and k are respectively the mean vector and covariance matrix of a Gaussian obedient mechanism. We assume that the prior distribution of 0, mu, is fixed, so that the only free parameters are pa, ka, k, and ka, using the notations from 5. Let O be the set of all pairs, mu, k, where mu and k denote respectively the mean vector and covariance matrix of an obedient mechanism. It follows from proposition 3.5 that O is characterized by the following constraints. The possible values for mu is reduced to the singleton defined by 8. K must satisfy the 2n linear obedience constraints. 9. K must be positive semidefinite. K equals st, r, 16. In particular, since mu is pinned down by the prior and 8, we will henceforth drop it from our notations and simply use O to denote the set of covariance matrices of obedient mechanisms. A general optimization problem over obedient mechanisms can therefore be written as sup fk, ko, 17, where f are 2n plus 1x 2n plus 1r. we focus on the case where f is a concave function, in which case, 17 defines a convex optimization problem due to ST, R, being convex. Reduction to symmetric mechanisms. We defined a symmetric mechanism in Definition 3.1 as one such that the distribution of A, 0, mu, is invariant under a relabeling of the players. In this case, Lemma 3.2 shows that the covariance matrix K takes a particularly simple form with only 5 degrees of freedom, O2, sigma A oj, sigma A, 0, sigma A, 0, for an arbitrary pair, I, J, N. With oj, we denote by O, CO the subset of O consisting of covariance matrices of obedient and symmetric mechanisms. Combining Remark 3.6 and Lemma 3.3, we have that KO, if 1, 2, sigma ILI, sigma AL, 2.
So this is, once we apply these two, right? We remove the variables to 3, sigma AIJ, sigma AI theta I, and sigma AI omega. This looks like an ellipse. First one doesn't look like an ellipse, to be honest, unless it doesn't look like an ellipse. Well, none of them look like an ellipse because they're all function of 3 variables. To look like an ellipse, like just being function of sigma AI theta I and sigma AI omega, is this is closer. This one definitely closer, sigma AI square. But you need to find sigma AI j. So one of them should always bind, so that we put the result to the other one. Find sigma AI j. Well, all of them. It is the case based on our structural result, I'm sure, because we had it before. One of them always is binding. Is all of them? I don't know. I guess, yeah. Then once we apply one,
where the first two inequality constraints express that K euro S, R, and the two linear equality constraints are from obedience. The following proposition shows that when both the prior distribution and the objective function f in 17 are symmetric, that is, invariant under a relabeling of the players, then we can restrict to symmetric mechanisms in 17 without loss of generality. Unsurprisingly, given that our game, too, is symmetric, we show below that both the welfare and revenue, in truthful mechanisms, are symmetric in K and the proposition applies. Proposition 4.1. Assume that the prior distribution on players type 0 is symmetric, and let for be a concave and symmetric function. Then, sup fk, ko, con, bo, toto, update proof to general K/. The proof of this proposition is presented in Appendix B and follows from a general symmetrization argument for convex optimization problems, lemma D.6. Essentially, we symmetrize a given mechanism by averaging its covariance matrix over all possible permutations of the players. Due to the concavity of F, this averaging can only increase the objective function. Note that the resulting symmetric mechanism is different from the usual lottery that first draws a permutation of the players uniformly at random and then applies the original initial mechanism to this permutation. While a lottery would certainly preserve obedience, a mixture of obedient mechanisms is still obedient. The resulting mechanism would no longer be Gaussian, because a non-trivial mixture of normal distributions is not normal. In contrast, our symmetrization argument is expressed directly at the level of the moments of the mechanism and exploits that the convexity of the constraints on the covariance matrix K. 17.
Wait, what are we showing, by the way? Structural result, the action recommendations are maximally negative correlated condition. The first inequality constraint becomes equivalent to point lies in, okay, exactly. Agree, fuck that, I don't want to read it. We also established that the point P must lie on the parameterized curve x lambda and y lambda. Y is sigma a omega x is that P is on it exactly where we find x lambda from that equation. There is we have it, the equation, everything fine, and that equation has a unique positive solution, everything fine. So when it is binding, we are inside. It's not binding, we are inside the ellipse, right? Okay, I'm good. On the parameterized curve, all right. Point P lies inside. We also established, well, when lambda is 0, we are inside, I guess. P is outside the ellipse for lambda equals 0. Once lambda gets bigger, we go inside. So we want to find the point that it hits for a positive amount of lambda. Okay, and the solution will be deterministic. And right, the solution will be deterministic. Either P is outside the ellipse or not, but since P converges to the center of the ellipse, what is the equation to find it though? It is binding. We found sigma ai theta I as a function of lambda, and we have the first inequality. I can open a new one. Why is it here? Yeah, that's the story, right? We are outside. If we are inside right away, it's just there. Okay, here this equation gives sigma ai theta I as a function of lambda. Then when the curve hits x lambda y lambda hits the ellipse here, once we substitute sigma ai hij based on this equality, this will be an ellipse based on sigma ai theta I and sigma ai omega. So this will be an equality. Substitute the value of sigma ai based on the value you gain from this equality. It will give us an ellipse. Then we are saying this is binding. We have sigma ai omega based on lambda. We have it based on lambda and other stuff. Based on lambda, sorry. We have sigma ai theta I also based on lambda. So this is an equality. Everything is a function of lambda. Therefore we can find the lambda from this equality, right? Sounds good, okay. What is 39? Bring it. Exactly. This is sigma A omega, sigma AI theta I, all good. Sounds good. Okay. If I want to code it, I compute sigma A theta I compute, but it is not a function of lambda. I don't have, let's assume we are gonna code it. We don't have sigma A theta I as a closed form function of lambda. How can we find lambda from this? However, there is no lambda here. Still sigma AI omega is a function of lambda, and I hope it's a cute function of lambda as it is here. It's a cute function of lambda, very good. So once we can compute sigma AI omega here, we can solve it. We can find sigma AI theta I. We don't have lambda. Lambda is what we are looking for, alright? Okay, I get what is the difficulty, right? RP lies inside a turbulent hole. Symbols are stationary. After this point, we are not gonna continue. Sounds good. So it can be that lambda is also 0. And we should find delta, the optimal delta. But let's do it one at a time. So either lambda is positive, we should find the lambda from the equation. Or lambda is 0, we should find the delta. When lambda is positive, delta is 0. Thanks for being patient. Yeah, I think next time we just dive into the code. Oops. Mish told me you love coding. Counter. I have to go somewhere. Oh, can stop recording.